Jeremiah is going to be, giving us is an expert in cryptography. He's going to be giving a talk about crypto. And recently, several of the PL people here at Purdue and several of the crypto people got a large grant from IARPA to work on sort of integrating PL concepts into secure multi-party communication, computation. And one of the joys of sort of working with them is learning all this cool stuff from the crypto folks. It's been a real treat. And I'm glad that everyone here can have a similar experience from Jeremiah in this talk. So, okay.
All right, thanks for the introduction. So as Ben mentioned, I've been working with several of my PL colleagues here at Purdue to work on multi-party computation. But today I actually wanted to talk about something completely different. And part of the hope here is just like we've had a fruitful collaboration working on MPC, perhaps I can interest some of you in this topic, and this will be the start of more fruitful collaborations. Okay, so I'm excited to tell you about memory hard functions and password hashing. So let me start off by motivating the problem. Probably most people here have to use passwords, and probably if you're like me, you have multiple different accounts that require you to create passwords. And so you have to come up with a strategy to create and remember all these passwords, and you want to balance security and usability, right? You don't want to get hacked, but at the same time, you don't want to tear your hair out trying to remember all these darn passwords. So of course, things are complicated because you're trying to remember these passwords in the presence of adversaries who might want to trick you into revealing your passwords. So you're trying to log into paypal.com, but whoops, this is actually paypal.com, and you just sent Paul your password. So of course, right, if you create and remember a bunch of distinct strong passwords, after this breach, you're still safe at all your other accounts. But the problem is not many people do this in reality. In reality, people tend to select the easy way out. They'll pick the usable strategy instead of the secure strategy, right? And they'll reuse their passwords and select weak passwords. So this talk, we're going to look at the issue of password storage. So here, what happens when I register for an account at PlayStation.com? I send over my username, my password. Okay, my password's not actually 123456, by the way, but you're welcome to try it. And what happens at PlayStation's end is they store a file which includes my username, a random value called salt, and the hash of my password appended with this salt value. Now, the reason for hashing the password is so that later, if there's a configuration error on PlayStation's end, maybe they forgot to protect against SQL injection attacks or buffer overflow attacks or whatever it was, an attacker might be able to break into their server, steal this password hash file, and at this point, the attacker's no longer limited by 3 guesses, right? He can try as many guesses as he wants to try to crack my password. The only limits for the attacker is just the resources that he's willing to invest trying to crack my password. Okay, so unfortunately, this is a common problem, and I have a wall of shame here. And in fact, we can see that password breaches at major companies have affected millions of users. Now, there's an incorrect claim on this slide, and the problem is that this shouldn't actually be millions of users. This should actually be billions of users. In fact, just one breach at Yahoo resulted in the leak of billions of password hashes. Unfortunately, people still pick weak passwords. So if you look at a word cloud based on the passwords that people chose, you'll see lots of popular options. And I want to highlight one here. Apparently there's a lot of people misspelling purple. They added this E on the end. I'm not sure what's going on, but that's an interesting question. So these problems are also, this is also a very dangerous problem. One reason why this problem is dangerous is that the hardware that's available to password crackers continues to improve. One of the reasons for this is that the hardware that a password cracker needs is very similar to the hardware that a Bitcoin miner needs. So here's a machine, the Antminer S9. It will compute the SHA-256 hash function 14 trillion times per second. So that's what the th per second means. And this machine is not even that expensive, right? If you've got a couple $1,000s, you could go on Amazon right now and buy one. So, right, of course, if people are picking weak passwords and the attacker can try 14 trillion guesses per second, this is going to be devastation, right? Most people's passwords are going to be cracked pretty quickly. So one of the natural questions then is, can we increase guessing costs for the attacker? Okay, so that's a natural question, and there's been a lot of attempts to do exactly this. One of the older approaches is simply called hash iteration. So instead of storing the hash, you store the hash of the hash of the hash of the hash. And if you iterate enough times, hopefully this function is more and more expensive to compute. So for example, when LastPass was breached, they were using 100,000 SHA-256 hash computations, which seems like a lot, right? That's a lot of iterations. Now, the problem is, if you take this ASIC, which can compute 14 trillion hashes per second, and plug it in, we're estimating that this is about $1 per billion password guesses that the attacker tries. And a billion is far more than the attacker needs to crack a majority of passwords. Okay, good. So here's the challenge. The challenge is that the cost of computing a function like SHA-256 is steadily declining over time. But at the same time, humans are not evolving to become more patient, right? So we can't just increase this hash iteration count and call it a day, right? There's some time threshold. If you have to wait a minute to authenticate, you're going to start to get a little bit antsy. And especially if you make a typo, you're going to be really upset. Okay, good. So our goal then is to design a moderately expensive hash function, which can be computed quickly on a regular personal computer and is still expensive if the attacker has an application-specific integrated circuit. Okay, so that's a challenging goal. How do we approach this problem? Well, one of the main approaches is to design something called a memory hard function. So the intuition for a memory hard function is we want a function where computation costs are dominated by memory cost. Right, so instead of having the attacker just use some small core on an ASIC to compute this function, we want the attacker to have to fill lots of memory and maintain lots of memory throughout the entire duration of computation. Right, so if we can do this, we can guarantee that this function is going to be expensive to compute even on customized hardware. After all, the DRAM chip that you have in your computer is more or less the same thing that the attacker could put on his ASIC. Okay? So now we have good constructions of memory hard functions. And in fact, one of the original proposals is called scrypt, and it was proven to be maximally memory hard. But there is a problem with scrypt, and the problem with scrypt is that it's vulnerable to side channel attacks. Right? So if you're evaluating this function on what is a very sensitive input, namely the user's password, and the attacker is able to somehow infer the memory access pattern, they might actually be able to learn something about your password. That's not such a great property for a password hashing algorithm to have. So recently, there's been a lot of focus on the design of something called a data-independent memory hard function. Intuitively, this is just a memory hard function that has the property that the memory access pattern doesn't depend on the input, right? So we have a static memory access pattern with a static data dependency graph. The actual output, of course, depends on the input, but the memory access pattern should not. Okay, and if this is the case, then we can defend against our side channel attackers. Okay, so there's a number of candidates for data-independent memory hard functions. There was, in fact, a whole competition which completed in 2015, and there were a number of entrants. Argon 2 won the password hashing competition, and it has a data-independent mode called Argon 2i, which is originally what they recommended for password hashing. They've changed their recommendations now for some reasons I'll mention later in the talk. So how does one define a data-independent memory hard function? Well, to define it, you need two things. I need to give you a graph, which is just a directed acyclic graph, which encodes the data dependencies, right? So here, this is telling me that label 3 depends on labels 2 and 1, right? So the label 3 is the hash of label 2 and label 1. So this DAG just encodes the data dependencies. And then I also have my compression function, which typically in crypto land we'll model as a random oracle to make our security proofs work out. Okay. So with this abstraction, we can actually forget about random oracles and just talk about evaluating a memory hard function as a pebbling game, right? So here, placing a pebble on a node means that you've computed that value and stored it in memory. Removing a pebble from a node means that you've freed that corresponding data label from memory. So of course, there's pebbling rules, right? I can't just start off by placing a pebble in the middle of the graph, right? Before I place that pebble, I have to have all the dependent data values in memory. The output of this function is the label of the last node. So the pebbling rule says that I eventually have to place a pebble on that last node. Okay? So here's just a simple example, right? Pebble node 1, then pebble node 2. Now I can place a pebble on node 3. At the same time, I might free up locations 1 and 2 to reduce memory. Now I can place a pebble on node 4, place a pebble on node 5, and I'm done. Okay, good. So now the question is, how do we measure the cumulative memory cost of a function? And one way to do this is by looking at the best pebbling of our graph, right? And how do we define best pebbling? We're going to look at a metric called the cumulative complexity of the graph. So in other words, we're just going to sum over all time steps. We're going to sum the number of pebbles on the graph at that particular point in time. Now, there's other metrics like space-time complexity where you take the product of running time times the maximum number of pebbles that are necessary. It's a nice metric to study, but it's not appropriate in our context because it doesn't amortize, right? So one of the nice things about this metric is that if I want to pebble 2 copies of the graph, which corresponds to computing this function on 2 password guesses, the pebbling cost is twice the cost of pebbling 1 instance of this graph, right? So that's a nice property that we require. Okay, so yeah, here's an example with the pebbling I showed you. You'd sum up all the cost and you get 7. So now our goal is to find a directed acyclic graph G on n nodes with a couple properties. One property is that we want the in degree of this graph to be constant. That's just so that we can use our hash function to compute the labels. We also want the running time to be proportional to the number of nodes, right? Which is only true if we have constant in degree. We also want the CC, cumulative pebbling cost, to be as large as possible. So we'd like it to be n squared over tau for some small value tau, right? Hopefully tau is a constant, but we'll settle for the best we can. Why is this the goal? Well, we're trying to maximize our cost for a fixed running time n, right? So n is our running time, right? We want to maximize the cost in terms of our running time n. Remember, users are impatient, so n is bounded. So we'd like the cost to be as large as possible within this constraint. Okay, so I've been working on memory hard functions for a couple years. Let me summarize a couple years of work in 2 bullet points. There's this combinatorial property called depth robustness, which is necessary and sufficient to build secure data-independent memory hard functions. So let me just briefly show you what depth robust graphs are. Right. So we say that ED reducible. ED reducible is the opposite of depth robust. If we can find a subset of nodes to delete, such that after we delete these nodes, the longest path in this remaining graph has length less than or equal to d. Right? So if that's the case, the graph is depth reducible. If that's not the case, we'll say the graph is depth robust. Okay, so here's an example of a graph that's 1-2 reducible. Right? If I delete one node in the middle, the longest path has length 2. Okay? Good. So what we know is that depth robustness is a necessary condition. Right? So namely, if you give me a graph that's not depth robust, then I can find a pebbling attack, which is strictly smaller than n squared, which we don't want. So then we can ask our existing IMHF candidates based on depth robust DAGs. I'm going to skip over this, but the answer is no. So we get attacks on Argon 2I and other IMHF candidates. And yeah, it's a similar story for basically any IMHF that was proposed prior to 2017. Okay, good. So the other part of the story is that depth robustness is sufficient. So if we can construct an ED depth robust graph, then the cumulative pebbling cost is at least E times D. In hindsight, the proof of this claim is pretty simple. It's half a page, and it greatly simplified a prior proof, which was about 10 pages long and was not as strong as this. But the implication here is we can build constant in degree graphs with cumulative complexity at least n squared over log n, which is pretty close to n squared, and beats the best prior bound by multiple log factors. And in fact, in an asymptotic sense, one can prove that this is the best you can do. So you can extend those pebbling attacks to really show that you can't do much better than this for any graph with constant in degree. Okay, now of course, something I want to highlight here, and this is moving to some of the open questions. I said there exists. Now, of course, you might be wondering, well, okay, there exists doesn't do any good. I actually need one of these graphs to build a memory hard function. So we actually can construct practical depth robust graphs. So I can give you a randomized sampling algorithm if you draw a graph from this distribution with high probability it's depth robust. Now, it's practical. We've actually implemented it. So you can tweak the Argon 2I source code, and the algorithm runs just as fast as Argon 2I, except now it's more secure. So yeah, empirical security analysis matches this intuition. Since I'm running short on time, I'm going to jump over that and look at some open questions, though. One of the main open questions in this area right now is, so far the results I've shown you have an asymptotic flavor, right? There's these omega terms, and there's these hidden constants inside the omegas. And you might ask me, well, what are the hidden constants? And the answer is sometimes we don't know, and when we do know, they're not very good. Right? So there are massive gaps between the provable upper and lower bounds that we can get. So the lower bound being the best concrete lower bound you can get, and the upper bound being the best concrete attack that we can get. So I guess months ago, I presented a new attack, which actually showed that one of these depth robust graphs was actually a little bit less secure than empirically we thought. So it's just a new attack that we had missed before, and it reduces the cumulative pebbling cost. Of course, we were also able to give an improved construction, which fixes the attack and is secure against a wide class of pebbling attacks. But what I'd like is a proof that this concrete graph is actually has high CC. Right? So one of the open questions is, and this is something I'd like to do, is instead of trying to do a pen and paper proof and prove that this graph is depth robust, can we actually use the computer to aid the analysis, right? So what I'd like is a computer program that takes as input the graph G, some parameters E and D, and outputs yes if we can verify that G is ED depth robust. And if it's not, or in some cases maybe it's not able to verify, that's okay. This is an NP hard problem, but I guess this is a community that understands that NP hard doesn't always mean that you can't do it, right? So if we can do this, there are many applications. Memory hard functions is just one application. Depth robust graphs are used in lots of other areas of cryptography, proofs of space and replication. This is one of the proposals to make blockchain and cryptocurrencies more eco-friendly by replacing proofs of work with proofs of space. You can also use them for error-correcting codes and for many other cool objects. So with that, I will close and take any questions.
Okay, we have time for one or two questions if anyone has any. You come to me.
So I guess I probably could have asked you this a little earlier than me. Instead, I will ask you now. And it might be a very dumb question. So why can't I just take something that is memory hard but not input independent and just run it through ORAM?
Oh, okay, that's a great question. So there's this crypto primitive called oblivious RAM, which takes a data independent or data dependent program and compiles it down into one that's computationally data independent. So the question is, could we take scrypt, compile it through an ORAM and run it? So one of the answers is that by compiling it through the ORAM, you introduce an overhead, right? So there's a log n factor overhead. And then if you do this, you actually get a construction that's worse than the best data independent memory hard functions. So it would improve on some of the prior constructions, but some of the most modern constructions is actually going to be worse. Now that is an intriguing question, though, is, can you use something other than an ORAM to build a computationally data independent memory hard function? I can't say a lot about it, but I just submitted a paper on that, exactly that topic with some of my grad students.
Yeah, and maybe as an extension of that question, in the same way that if I have some domain knowledge, I can do better than just taking something and running it through ORAM to get memory independence. Is this something that can be generalized? If there's other computations that I want to become data independent, where the standard solution is to run it through ORAM, is it possible that there's some other transformation that we should be using instead?
Yeah, I mean, that's a great question, right? So ORAM is a very general purpose compiler to take your data-dependent execution trace and get a computationally data-independent execution trace. But for a lot of programs, this may not be the optimal thing. And for memory hard functions, we can do something better. Yeah, I don't know how to generalize it at this moment, other than on a case-by-case basis. But if one could find a more principled or systematic approach to do this, that would certainly be of interest.